We have a new topic today regarding design of stirrups, G2 shear and torsion. Design of stirrups. Just to remind you what was the story, because we are in a very long story in this course. Guys, in structure analysis, we learned for any external forces, we have something called internal forces. These internal forces looks like axial force diagram. We will cover this next week. We have bending moment. We cover this before exam 1. If you have a moment, if you have a beam with external load, distributed load, for example, I can draw bending moment. I can design my beam. I can get the area steel if you have bending moment. And we learned how to calculate the own weight of the beam and how to draw bending moment, how to design each cross section. So we are done with the bending moment. Also, we learned in structure analysis last semester, we have something called shear force diagram. And probably in strength of material or mechanics of material, you learned something about torsion. Torsion, which is torque, coming from torque. Anyway, I will cover this next time, next meeting. I will focus today on shear force diagram. So just to remind you, if you have a beam from structural analysis, this beam with uniform distributed load, we have something called bending moment. And this value, W, L square divide 8. This is called bending moment diagram. We learned everything about this diagram. How can we use this value of moment? How can we figure out the area steel? How can we figure out the design of your member related to bending moment? Today, we are talking about another diagram we learned from structure analysis, which called shear force diagram. Guys, your bending moment is supported in the beam by this longitudinal reinforcement. And we learned how to figure out these reinforcement. Your moment is coming like this. So we have tension in one side and we have compression on the other side. Your steel reinforcement coming to support this tension, because concrete cannot do this. If you are talking about shear, we have something different, which called stirrups. Can you watch this rectangle reinforcement? This rectangle reinforcement, which is repeated uniformly along the beam with distance or spacing equal S. Or sometimes your longitudinal reinforcement pinned like this. Can you watch this one with 45 degrees bent with 45 degree? The main reason for this bend to support shear force. But we highly recommend to use stirrups to support this shear. Let me explain it to you a little bit. You have a beam, looks like this. This column supporting your beam with a reaction. This beam has uniform distributed load. What do you think? The uniform distributed load would like to push this beam down. That's right. That's right. And this reaction would like to push this part of the beam up. So I'm gonna expect something here. I'm gonna expect crack like this, because the uniform distributed load will move this part of the beam down. And this reaction from the column would like to move this part of the beam up. So we can expect crack at this location. So we have two options. The first option, your longitudinal reinforcement at this location will be pinned like this. In the real life, like this. Can you watch it? Here you go. This is called bent bars. The main reason for that, if you have a crack, your reinforcement must be perpendicular to this crack to prevent it. Put it in your mind. Put it in your mind. If you have a crack in concrete, your steel reinforcement must be perpendicular to this crack to prevent it. Just also to make it clear for you. If you have a beam and this beam is supported by two columns, if you have uniform distributed load, I believe this beam would like to be broken with cracks at the mid-span, vertical cracks. So your steel reinforcement must be perpendicular to these cracks. So this is the reason why we are putting steel reinforcement like this at the bottom of the beam. So your reinforcement must be perpendicular to your crack. But for shear, this is for moment. I'm talking about here about moment. Your cracks will be vertical cracks at mid-span, because your maximum moment at mid-span, here is the W, L squared divide 8. So at maximum moment, we can expect a crack. But for shear, different situation. Your cracks will be inclined crack. So we have one option. The first option, to make your reinforcement bent like this. Or we have another option. The other option, to put stirrups, vertical stirrups. These stirrups will help to prevent these cracks. One of you will ask me a good question. You told us the cracks of shear looks like this. And based on this photo, your stirrups are vertical stirrups. Like this. And you just told us it's recommended to make reinforcement perpendicular to the crack. That's right. So do you think these stirrups will be efficient? Probably not. The most efficient crack, the most efficient stirrups, if you have cracks like this, the most efficient stirrups must be looks like this. But it's very hard in the real life, in the site, it's hard to apply stirrups with angle with the horizontal. The most common type or the most common method of construction to make your stirrups vertical stirrups. But the most efficient application of stirrups must be inclined. Why inclined? To be perpendicular to the inclined crack. Any question for this point? From this point, I need you to learn something. We have something called shear force diagram. This shear force diagram is resisted by something called stirrups, or in some cases, bent bars. Yes. Most of the time, we cannot apply this stirrups with angle. 90%, probably 95% of all stirrups are vertical stirrups. But the stirrups is still efficient, can resist this inclined. But if you make it inclined, the stirrups, inclined stirrups, it will be more efficient. From this point, it's very important to understand this point. Your reinforcement must be perpendicular to your crack. Probably one time after your graduation, you have interview for a job. And someone will ask you, hey, if we have a beam like this, and we have a crack in this beam, we have crack in this beam like this. How can we resist this crack? Or we have crack like this. How can we support this crack? Remember, your answer will be, for the vertical crack, we must apply horizontal reinforcement, which is the longitudinal bars, like this one. For inclined crack, we have two options. The first one, you need to apply reinforcement perpendicular to this crack, so you can use bent bars. Or I can apply vertical stirrups to resist this cracks, or these cracks. So both in your mind, we have a very good relationship between cracks and reinforcement. The main function of reinforcement to prevent crack. Okay? Any questions so far? How to understand this concept is very easy, because how to calculate the stirrups and the spacing, piece of cake. Piece of cake, nothing. But you need to understand, if you have a shear, we have a stirrups. By the way, this reinforcement, this one, can be called longitudinal reinforcement. Sometimes we can call it main reinforcement. But if you are talking about stirrups or bent bars, you are talking about something called transverse reinforcement or stirrups or shear reinforcement. All of these expressions you have to be familiar with. Longitudinal reinforcement, main reinforcement to support your moment. Transverse reinforcement, shear reinforcement, stirrups, bent bars to support your shear force. Okay? We learned how to figure out the reinforcement for moment for different cases. T-section, rectangular section. If you have moment, I can figure out steel reinforcement. If you have a steel reinforcement, I can figure out the design moment. We are done with this part. So we need to focus on shear force. Do you think, my question is, Do you think shear is resisted only with these stirrups? No, we have concrete. Concrete is still good in shear. So shear force is supported by concrete. Part of this shear is supported by concrete and the other part by stirrups. Concrete is very weak in tension. If you are talking about tension, concrete will be cancelled. But we are talking about shear. Concrete is good with shear. It's not very good, but it's still good. So your nominal resistance, the nominal or theoretical shear resistance or strength of beam can be divided by VC, which is the part resisted by concrete, and VS, which is the part resisted by shear reinforcement. We can call it stirrups. Remember, we don't use nominal strength or nominal shear strength. We are not using this term. So we need to multiply this nominal by phase reduction factor to get something called design shear strength. So design, this term can be called design shear strength. I believe we covered this before. Do you remember? You learned how to calculate nominal moment, which equal area steel F yield times D minus A divided 2. Do you remember that? I told you this moment called nominal moment. We are not using this value in design. We need to multiply this nominal moment by phi. Do you remember how can we figure out the value of phi? Based on the value of this strain in steel reinforcement. In our case, in this case of shear, it's very more simple. Phi equal constant value, 0.75. We don't need to figure out what is the value of phi for shear. It's only 0.75. If you are talking about shear and torsion, we will cover this later. But for shear, your phi is 0.75. So once you figure out the value of VC, the value of VS, I can figure out the value of VN, then multiply it by phi, then I can figure out the shear, the design shear strength. We have something called V ultimate, which is coming from structure analysis. Structure analysis. I told you from structure analysis, we have something called shear force diagram. So this shear force diagram will give you V ultimate. These equations will give you phi Vn. All the time, your shear from or ultimate shear from structure analysis must be smaller than or equal this design to be safe. So the key right now, how can I figure out the part resisted by concrete and the part resisted by stirrups? We have here two equations. That's it. We are done. According to ACI, the shear resisted by concrete equal 2B web D square root F prime C. That's it. Just to remind you, here is the cross section of the beam. Here is the steel reinforcement. We don't care about it right now. We are in the case of shear. But from this cross section, I need to figure out what is the value of this depth, this term. What is the value of this width, which called B width, this term. Sometimes we call it B without W. And square root F prime C, this value in PSI. 4,000, 3,000, 2,500, 5,000, whatever given in the problem. This is the part or the shear strength provided by concrete. shear strength provided by stirrups equal AV F yield depth divide S. What is the meaning of S? Do you remember? Spacing. We have stirrups spaced uniformly. So the spacing between this one and this one is S. So S is the spacing. AV is the total area of the stirrup legs. I'm sorry, stirrup legs? Yeah. Your stirrup in the real life looks like this one. That's right? That's right? So, how many legs do you have here? 1, 2. This leg has area. This leg has another area. So area V is the total area of the stirrups leg. This cross section plus this cross section. Sometimes your stirrups looks like this. So how many legs do you have? 1, 2, 3, 4. So area V will be 4 times area of one leg. So please remember, area V is the area of the stirrup legs. Okay, I can figure out how many legs I have. So what is the area of one leg? Okay, based on the size. Most of the time we are using number 3 or number 4 in stirrups. Number 3 has area 0.11. Number 4 has area 0.2. If you cannot remember this value, go back to your table. Do you remember that table? For number 3, the area of the bar 0.11. Number 4, area of the bar 0.2. So most of the time, your stirrups made from number 3 bars or number 4 bars. So area V, I can get it. S stirrups. What is the spacing between stirrups? So I can figure out VS. Once you get VS, once you get VC, add them together to get VN. Once you calculate VN, which is called nominal or theoretical shear strength, we need to get the design. So we need to multiply this VN by phi, which equal 0.75. So what do you think? Yeah. So I think it's very easy. Very easy. But these two equations are very important. Be careful about how many legs of the stirrup. Most of the time, 2 legs, the regular one, rectangle. But sometimes we have more complicated stirrups with many legs. If you have very heavy shear. Most of the time, the design bars for shear or for stirrups, number 3 or number 4. Most of the time, 99%. Steps of design. We need to understand what is the steps. But before saying steps, okay, if everything is given, what you mean by everything? Yeah, everything. The stirrups is given. The spacing is given. The cross section is given. So everything is given. I can figure out the design strength, the design shear strength. I will use this value plus this value to figure out this value, multiply this value by phi, so I can figure out the design and make a comparison to make sure this beam is safe or unsafe. That's easy. That's fine. But sometimes we need to design. What you mean to design? We need to understand, we need to figure out what is the value of S. S is unknown. What is the design value or what is the size of this stirrups? Number 3 or number 4? or what? What you mean? So this is a design. So let's start. If you would like to design, first step, you need to draw shear force diagram from structure analysis. And this shear force diagram will help you to figure out the value of V ultimate, which is the applied shear force. To be more specific, applied ultimate shear force. Then I'm gonna calculate the value supported by concrete. Shear strength of concrete, but not nominal, the design. If you would like to get a design, so you need to multiply VC by phi, and your phi is 0.75. VC, here you go, this one. I'm gonna assume the diameter of the used stirrups. We have two options, number 3 bar or number 4 bar. Number 3 bar, so the area of one leg will be 0.11. Number 4 bar, the area of one leg, 0.2. So if you figure out how many legs, I can figure out the value of area V. So size of the stirrups will be assumed. So the only unknown, what is the spacing between stirrups to support this shear? We have 3 cases. Very important. We have 3 cases according to ACI. First case, F. First case, F. V ultimate from the structure analysis smaller than or equal phi VC from concrete divide 2, no stirrups required. Concrete is enough to support that shear. We don't need to put stirrups. F V ultimate smaller than or equal phi VC divide 2. Your decision, no stirrups are required. Concrete will be enough. Second case, if V ultimate from structure analysis greater than phi VC divide 2, but smaller than or equal phi VC. That means we need minimum stirrups because concrete is still good, but we need stirrups minimum just in case, because you are critical a little bit. So we are going to use minimum. So ACI tell you, hey, we have 2 values for the spacing, this one or this one. Area V time F yield divide 50 B web, or area V F yield divide 0.75 B web square root F prime C. Which one I'm gonna use? The smallest one, the smallest value for this spacing or this spacing. Third case, if V ultimate from structure analysis is greater than concrete strength, that means concrete cannot support alone. We need to add stirrups with design. So I'm gonna figure out the value of VS supported by stirrups equal V ultimate divide phi minus VC, and then I can figure out the spacing from this equation. So guys, if you would like to figure out the spacing, the required spacing between stirrups, we need to go through these steps. First step, what is the value of? Sometimes it's given in the problem, sometimes no. We need to go back to structure analysis and draw shear force diagram to figure out V ultimate. Second step, what is the design shear strength for concrete? Phi VC. Third step, you need to assume what is the bar size used for these stirrups to figure out the value of area V. We have three situations. Start one by one. If you are not here, check this one. If you are not here, then you are in the third one. The first condition, if V ultimate is smaller than or equal this value, no stirrups required. Don't put any stirrup in this beam. Concrete is enough. But if your V ultimate greater than this value and smaller than this value, you are critical. Concrete is still good. Concrete is still good, but you are critical. So I'm gonna put minimum reinforcement or minimum stirrups. Your spacing between stirrups will be this value or this value, the smallest one. The third one, no, concrete cannot support shear. We need to add serious stirrups. So we need to figure out the shear supported by stirrups. Then I can figure out the spacing between stirrups. So what do you think? Yes, Faye always, Alan. Faye always 0.75. Any question? Okay. So I just to remind you, it's very important to understand this long story. Inside any reinforced concrete beam, we have different type of reinforcement. The first one, longitudinal, related to bending moment. We are done with this part. Right now, we are talking about something called stirrups, vertical stirrups. These stirrups to support shear force diagram on this beam. Finally, the final conclusion, we are going to assume what is the bar size, number 3 or number 4, and then we can figure out the spacing. This is the final conclusion in your design. Assume one parameter and figure out the second parameter. Okay? So assume the diameter of the stirrups. Then I can figure out the spacing of these stirrups. Once you figure out the diameter, or you assume the diameter, and you figure out the spacing, you are done with your design. This one is for a check, because we have maximum spacing. You have no choice to exceed this spacing, because someone will say, hey, my design gave me this stirrup and another stirrup, and this spacing equal 2 feet. No, we have, or 3 feet, or 4 feet. No, we have maximum spacing. You have to respect. You cannot exceed this limit. For example, your maximum spacing, the smaller between depth divide 2 or 24 inch. If you are in this case. If you are in this case, so we have this maximum spacing or that maximum spacing. We will check these during our first example. Let's do this example first. This one. Example number 1. Step by step. We have a beam, and this beam has a dead load equal 2.5, but this dead load does not include the weight of the beam. So you have more experience right now. You are genius. You are professional. So on weight of the beam equal 16 divide 12 time 30 divide 12 time 150. That's right. So 16 divide 12 time 30 divide 12 time 150. Your value is 500 pound per foot. That means your dead load total will be 2.5 plus 0.5. Remember, 500 is bound. It will be 0.5 kb foot per foot. So your total dead load will be 3 kb per foot. Your live load will stay the same, 3 kb per foot. So can you tell me what will be the ultimate load value? Yeah, it will be 1.2 dead load plus 1.6 live load. Your final value will be 3 times 1.2 plus 3 times 1.6, 8.4 kb per foot. The total length is 24, 8.4. So I will go back to structure analysis. Just to remind you, we have a beam with total length 24 feet. And we have uniform distributed load. How much? 8.4 kb per foot. If you would like to draw shear force diagram, we have here reaction, and we have uniform distributed loads. We have equivalent. This one will be 201.6. This reaction will be 100.8, 100.8. I just divide this one by 2 because it's symmetric. Go up from your left. You are here. From my left, I will go up 100.8. Move dotted until you found this equivalent. I will go down. Then make sure keep walking until here you will close to 0. So your shear force diagram looks like this. This one will be 100.8 also. This is called shear force diagram. That means your V ultimate equal, what is the maximum value of shear? Here is the values of shear. What is the maximum value? I don't care about positive or negative. We don't care about signs. In shear, we don't care. Our concern, what is the value? What is the absolute value? Or what is the absolute maximum value? It's 100.8 kb. From structure analysis. This is the reason why structure analysis course is required before this course. Without a structure analysis, many parts will not be figured out. Any question for this point? Guys, also, I don't have any problem. If you have issue, you can use RISA. But this beam is very simple. So we don't need to use RISA. It's very easy. Okay? So your V ultimate equal how much? 100.8 kibs. Do you remember what was the first step? Wow. Draw shear force diagram to figure out the value of V ultimate. Second step, calculate the design shear strength of concrete. VC equal or phi VC will be phi. I think what was the equation for this one? Do you remember? Where? Here you go. This one. 2B web D square root F prime C. Guys, remember, VC alone equal this term alone. But I'm looking for design shear strength of concrete, so I added phi on the other side also. What was the value of phi? 0.75. You don't need to figure it out. 0.75 is a constant number. 2 P web, this width 16. Depth, what is the depth here? I'm gonna assume 2.5 cover, so it will be 27.5 or 2 inch cover, as you like. So I assumed it 2.5. So 27.5 time square root f prime c. F prime c is given 3000. Very easy. Very easy. So 0.75 times 2 times 16 times 27.5 times square root of 3000. This value equal 36,149.7 pound. Can you convert it to kip? Yeah, I will divide it by 1000. It will be 36.1 kip. Phi VC. 36.1 kip. The value coming from this equation will be in pound. Go ahead and divide it by 1000 to be in kip. I am done with this step. I calculated the design shear strength. Go ahead and assume what is the diameter of the stirrups. So what do you think, guys? Go back to the problem. Probably they are given. Yeah, the problem give you a hint. Use number 4 stirrups. So please go ahead and respect what's going on in the problem. The problem said go ahead and use number 4 stirrups. So stirrups will be number 4. How many legs do you have? Can you watch this cross section which is given? How many legs? 1, 2 legs. So area V will be 2 legs time. What is the area of number 4? Open your table. Number 4 bar size has 0.2 area. So time 0.2, your area V will be 0.4 inch square. So the third step, we need to assume diameter, but in our case, diameter is given or bar size is given in the problem, but it's not given. It's not given. You can assume what you want, number 3 or number 4. Then I can calculate area V, which is number of legs time area of 1 leg. Any question so far? Okay, keep going. We are probably in this case or this case or this case. Let's see. V ultimate is 100.8. Can you tell me what is the value of phi VC divided 2? Phi VC equal 36.1. Divide 2, it will be 18.05. No. Okay. Phi VC equal 36.1. No. So I believe V ultimate, which is 100, is greater than phi VC. V ultimate greater than phi VC, because this term is 36, this term is 100.8. So you are in this case V ultimate greater than phi VC. So we still have only 2 steps. First step, VS equal V ultimate divide phi minus VC. So VS equal V ultimate divide phi minus VC. V ultimate 100.8 divide phi 0.75. What is the value of VC? Do you remember? 48.13. Wow, how can I get this number? Guys, for phi VC equal 36.1, but we are looking for VC only. Go ahead and divide this number by phi. It will be 48.13. So I can figure out the value of VS. Your value will be 86.27 kips. Last step, your spacing equal area V, F yield, depth divide VS. So your spacing equal area V, F yield, what? Depth divide VS. What is the value of area V? 0.4. Do you remember? 0.4. What is the value of F yield? It's given in the problem. 40,000. What is the value of depth? 27.5. What is the value of VS? 86.27 time 1,000, please. Why time 1,000? Because this value in kip and the F yield in pound per inch square. So this one in kip, this one in pound, I need to convert from kip to pound. So I multiplied by 1,000. Your final answer of S will be 0.4 times 40,000 times 27.5 divide this number times 1,000. It will be 5.1 inch. 5.1 inch. That means in this beam, I have to put vertical stirrups with number 4 size at 5.1 inch. It's written like this. In the shop drawing layout or something like this, it will be written like this: number 4 at 5.1 inch. How can I read this expression? Number 4, which is the size of bars. At means spacing every, each 5.1 inch. 5.1 inch. So if you would like to make it more easy for construction, so you can 5.1 will be 5. Number 4 at 5 inch spacing. It will be more easy. So your design of a stirrups for this beam based on the shear force diagram, and you assumed number 4 size, I'm gonna take every 5 inch stirrups spacing. If you check the maximum spacing, I believe 5 inch will be within or smaller than maximum, because you are talking about 24 inch or depth divide to something very, very high. So I believe 5 inch will be good for the maximum stirrups check. So guys, what do you think? It's very easy. Design for shear, it's very easy. Do you have any question? Do you have any question? Okay. Yeah.
I have a question.
Yeah.
For V ultimate, how did you like determine that exactly? So let's say if we had a beam that didn't have a uniform distributed load, and we had different values for reactions and etc. How would you determine V ultimate from there?
What you mean by the ultimate shear? You mean?
Yes, ultimate shear. Yes.
Okay, actually, ultimate shear, to figure it out, you have to draw shear force diagram. Sometimes you have shear force diagram like this, for example, like this, for any reason. So once you draw your shear force diagram, go ahead and search for the maximum value. What is the value here? What is the value here? What is the value? I don't care which one is positive, which one is negative. I don't care about sign. What is the value here? What is the value here? What is the value here? And get the maximum one. So V ultimate is the maximum value from shear force diagram. Because sometimes your beam has uniform, has concentrated, has moment, has something different. So you have to draw shear force diagram first to figure out the maximum value of shear. But if your beam is simply supported with only uniform distributed load, your shear will be the same like your reaction. It's only special case. Simply supported, uniform distributed load only, your maximum shear will be the same value for reaction. You don't need to draw shear force diagram. This your question, Burak?
Yes, sir. That's exactly what I meant. Thank you.